Somewhere off the coast of the Bahamas, divers are watching something that shouldn't be possible. A steel frame, lowered into the ocean weeks earlier, is no longer steel. It's covered in stone. Not poured, not mixed, not trucked in from a quarry. Grown out of seawater and sand using nothing but electricity. No cement truck ever showed up. No bag of Portland cement was cracked open. And yet, right there, under 20 feet of salt water, minerals dissolved in the ocean are locking themselves together into something that behaves almost exactly like rock. Why has almost nobody heard about this? Before we go any further, let's be honest about what this video is and what it isn't. This isn't a magic trick, and it isn't a one-size-fits-all replacement for everything you know about building materials. What you're about to hear is based on real scientific research and documented history, explored here strictly for educational and informational purposes. This is not a guaranteed method for your specific project, your specific soil, or your specific climate. Results vary depending on materials, water chemistry, equipment, and local conditions. Some of what we'll cover involves electrical current, and any hands-on experimentation with electricity, minerals, or structural materials should always involve proper safety precautions. And where relevant, a licensed professional, an engineer, an electrician, or contractor who knows your local building codes. We're not telling you to rip up your driveway. We're telling you a story about a process that's real, that's been tested, and that raises a genuinely interesting question about the future of how we build. With that said, let's get into it. Here's the concept in plain terms. Seawater is packed with dissolved minerals, mostly calcium and magnesium. Historically, humans have looked at seawater as something that corrodes metal, erodes coastlines, and generally works against construction, not for it. But in the 1970s, a German architect named Wolf Hilbertz asked a strange question. What if you could use electricity to pull those dissolved minerals out of seawater and force them to build something? He ran a low-voltage electrical current through a submerged steel frame. The negatively charged frame started attracting positively charged minerals floating in the water. Slowly, over weeks and months, calcium carbonate and magnesium hydroxide began crystallizing onto the metal. Layer by layer, the structure thickened. What started as a bare steel skeleton became coated in a stone-like material, sometimes referred to as mineral accretion. But here's where it gets interesting. This wasn't just a lab curiosity. Researchers found that the resulting material in some tests showed compressive strength comparable to concrete while forming itself underwater, using energy that could come from solar panels or wave power. No mining, no cement kiln, no massive carbon-heavy manufacturing process. And this is where most people stopped looking, assuming this is some obscure ocean-only phenomenon. It isn't, because concrete itself has a history that most people never learned in school. Ancient Rome built structures that have survived nearly 2,000 years. The Pantheon's concrete dome is still standing, using volcanic ash, lime, and seawater in ways modern engineers are still studying today. Researchers have explored how Roman concrete actually gets stronger over time when exposed to seawater, because of mineral reactions happening inside it. That's the opposite of how modern concrete behaves, which tends to weaken with prolonged saltwater exposure. So the ancients were already working with the idea that minerals, water, and time could build something durable, long before industrial cement plants existed. Modern electrical mineral accretion is, in a sense, a rediscovery of that same instinct, using electricity instead of volcanic chemistry to speed up a natural mineral locking process. Over time, as industrial cement production scaled up in the 20th century, faster and cheaper became the priority. Simpler, slower, mineral-based methods became less mainstream, not because they didn't work, but because they didn't fit the pace of modern construction demand. Here's what matters. That doesn't mean the science stopped being real. It just means it stopped being commercially convenient. So how does the science actually work, in plain language? Think of seawater as a soup loaded with dissolved calcium and magnesium ions. When you run a mild electrical current through two electrodes submerged in that water, you create a chemical pull. The cathode, the negatively charged side, starts attracting those positively charged mineral ions. As they arrive, they react with the water's natural chemistry and begin forming solid calcium carbonate, essentially a limestone-like mineral, and magnesium hydroxide, which acts almost like a natural binder. It's similar, conceptually, to how a battery terminal can slowly build up corrosion, except here that corrosion isn't rust. It's a controlled, engineered mineral coating that hardens over time. Researchers have explored using this exact process, often called electrodeposition or mineral accretion, to grow artificial reefs, repair coastal structures, and even attempt small-scale construction elements. Environmental teams have used it to help regenerate coral reef structures, because the resulting material provides a stable, rock-like surface that coral can actually attach to and grow on. But the real question is, can this leave the ocean? On land, engineers and researchers have been exploring a cousin of this idea for years, techniques broadly known as electrokinetic soil stabilization. Instead of seawater, you're working with soil that naturally contains moisture and dissolved minerals. A low voltage current is applied through electrodes placed in the ground. Over time, this can encourage certain minerals to migrate and bind, in some cases increasing soil strength and reducing erosion, particularly in loose, sandy, or unstable ground. This isn't the same as mineral accretion, turning sand into a full block of stone overnight. It's a slower, more gradual process, and results vary heavily based on soil composition, moisture content, and mineral availability. In some cases, researchers have used it for shoreline stabilization, embankment reinforcement, or reducing erosion around vulnerable structures. For the average American homeowner, this isn't going to replace your foundation contractor next week. But it's part of a growing field of research into low-carbon, low-energy alternatives to traditional cement, which, for context, is responsible for a significant share of global industrial carbon emissions. Cement production requires burning material at extremely high temperatures. Electrical mineral accretion, by contrast, can potentially run on solar or renewable power at ambient temperatures. For preppers, off-grid builders, and coastal property owners specifically, the appeal is obvious. If you live near salt water, near a marina, or manage erosion-prone land, some of these principles, in controlled, professionally guided settings, have been used to help stabilize shorelines and reduce soil loss. But limitations matter here. This process is slow. Building a meaningfully thick, load-bearing structure through mineral accretion can take weeks or months, not hours. It also depends heavily on water chemistry. Freshwater doesn't contain the same mineral density as seawater, so results on land, away from the coast, are far less predictable. And any project involving structural safety, especially anything supporting weight or building, should always go through a licensed engineer. Before we go further into the practical side of this, I want to hear from you. If you live near the coast, drop your state below. Florida, California, the Carolinas, the Gulf Coast, wherever you are, I want to know if you've ever seen mineral buildup like this on docks, pilings, or old marine structures without realizing what was actually happening. And if you've ever dealt with erosion, unstable soil, or shoreline damage on your own property, tell us about it. What did you try? What worked and what didn't? If topics like this, forgotten methods, overlooked science, practical self-reliance, are your kind of thing, consider subscribing. This channel exists to dig up ideas that got quietly pushed aside by modern convenience and bring them back into the light. Now, let's talk about how this actually gets used in practice. To be clear up front, full-scale mineral accretion setups involve marine-grade equipment, power supplies, and safety protocols that go beyond a casual weekend project. This part is about understanding the process, not a step-by-step build guide for structural work. The first thing to understand is the environment. This process depends on mineral-rich water, seawater, brackish water, or mineral-heavy groundwater. Freshwater alone typically won't produce strong results. Next comes a low-voltage power source. Documented projects have used solar panels, marine batteries, or small renewable setups, since the voltage required is relatively low compared to industrial electrical use. Any electrical work near water carries real risk, and it should only be attempted with proper insulation, waterproof connections, and, ideally, guidance from someone experienced with marine electrical systems. Then there's the frame or structure. In real-world projects, a steel mesh or rebar frame is submerged and connected as the cathode, while a secondary electrode acts as the anode. Over time, mineral buildup forms across the frame's surface. Patience matters enormously here. This is not a fast process. Visible buildup can begin within days, but meaningful thickness and strength typically take weeks to months, depending on water conditions, current strength and temperature. And finally, monitoring is constant. Researchers and marine builders regularly check current flow, mineral buildup rate, and structural integrity throughout the process, adjusting as needed. For homeowners interested in the underlying science rather than large-scale building, this is primarily valuable as a research topic, a lens into how future low-carbon materials might be developed rather than something to replace a foundation pour this weekend. Let's be balanced about this, because hype without honesty helps nobody. This process is not going to replace concrete for most modern construction anytime soon. Concrete is fast, predictable, and extremely well understood by engineers everywhere. Mineral accretion and electrokinetic stabilization are slower, more experimental, and far more dependent on environmental conditions like water chemistry, mineral availability, and temperature. It's also not equally effective everywhere. Inland freshwater regions face real limitations compared to coastal or saline environments. Soil composition varies wildly from state to state, and what works in a sandy coastal environment may behave completely differently in clay-heavy or rocky inland soil. Maintenance and long-term durability are still active areas of research. And for anything involving structural safety, a foundation, a retaining wall, anything supporting weight or protecting a home, professional engineering advice isn't optional, it's essential. What this technology does offer is a genuinely interesting case study in low energy, low carbon material science, and a reminder that some of the most promising solutions might not be new inventions at all, but old principles, minerals, water, and electricity waiting to be looked at differently. Everything you heard in this video is shared strictly for educational and historical purposes. It's not engineering advice, it's not a construction manual, and it's not a promise that this method will work the same way in your backyard as it does in a research lab or a coastal reef project. If you're ever considering anything involving structural stability, electrical systems, or major property changes, please consult a licensed professional in your area. We tell these stories because somewhere between ancient Roman seawalls and modern marine science, there's a pattern. Humans quietly figuring out how to work with nature instead of against it, long before it became profitable to remember. Concrete probably isn't going anywhere anytime soon, but the idea that stone can be grown, not just poured using nothing but electricity and the minerals already sitting in water all around us, that's the kind of forgotten knowledge worth holding on to. If this kind of story pulled you in, there's another one waiting. Next time, we're going deeper into a method almost nobody talks about anymore, one that early builders used to waterproof entire structures without a single drop of modern sealant. Subscribe, stay curious, and I'll see you in the next one.